Millions of years ago, the Indian tectonic plate crashed into Eurasia. The impact shoved barren rock thousands of feet upward, creating the jagged Himalayas. That collision established the rules for the subcontinent's modern hydrology. Today, India is sustained by 14 major river systems that handle nearly 60% of its available surface water. Every drop of that water follows a path strictly dictated by the geological relief. The total land area drained by a single river system is known as a drainage basin. When an elevated area, like an upland ridge, sits between two adjacent basins, it acts as a physical barrier. Rain hitting the peak splits, sending water down opposite slopes into different river networks. This topography is called a water divide. Two of these massive divides, the Ambala Ridge in the north and the Western Ghats in the south, act as the master topological switches, routing almost all of the subcontinent's surface water. These divides effectively split the country into two massive hydrological engines, the Himalayan engine in the north and the Peninsular engine in the south. The Ambala Ridge sits squarely between the massive Indus Basin and the Ganga Basin. It acts as a wedge, forcing the two systems to flow away from each other. Further south, the Western Ghats form a sheer, continuous wall along the western coast. Even though many southern rivers originate just a few miles from the Arabian Sea, this barrier forces them to flow hundreds of miles eastward across the entire landmass to reach the Bay of Bengal. Before we can examine human infrastructure, dams, or international water treaties, we have to understand these physical constraints. In this landscape, the path of every river is a forced choice, determined by the architecture of the bedrock. The Himalayan engine drives the Indus, the Ganga, and the Brahmaputra. These are perennial rivers, running year-round because they are powered by both heavy monsoon rains and the meltwater from over 5,000 high-altitude glaciers. In their steep upper courses, these rivers possess immense velocity. They tear through mountain ranges, carving deep, V-shaped vertical gorges straight into the rock. This process is visible at the very origin of the Ganga. The river does not start as a single massive channel, but rather forms from the convergence of several mountain headwaters. The Bhagirathi and the Alaknanda streams physically collide at Devaprayag to officially form the Ganga River. This violent high-altitude collision and the continuous scraping of the riverbeds generate a massive suspended load of silt and sand that is carried downstream in the water. The upper course of the Himalayan engine is a high-energy system, defined by deep cuts and the relentless, continuous transport of geological material away from the peaks. Eventually, these high-velocity waters exit the mountains and hit the flat expanses of the northern plains, where they suddenly lose their momentum. With the sudden drop in slope, the rivers can no longer carry their heavy sediment loads. They are forced to snake back and forth in wide, sweeping meanders, dropping millions of tons of silt along curve. This rapid, continuous deposition clogs the riverways. The water fractures into braided channels, the riverbeds physically rise, and the rivers frequently shift their entire courses to find easier paths. The result is intensely destructive. Every year, the Brahmaputra becomes so choked with its own silt that it is forced out of its channel, overflowing its banks and submerging massive tracts of human settlement and agriculture in Assam. The material that isn't dropped in the plains is carried all the way to the coast. This terminal deposition builds massive, fast-growing landmasses, like the Sundarbans Delta, where the Ganga and Brahmaputra meet the Bay of Bengal. The floods and deltas of the plains represent the terminal physical result of glacial erosion occurring thousands of miles away. South of the plains, the Peninsular engine operates under a different set of rules. Rivers like the Godavari, the Krishna, and the Mahanadi lack glaciers. They are pluvial, meaning they rely entirely on seasonal rainfall. These rivers run through ancient bedrock. They possess older, shallower, and shorter courses. Having already graded to their base level, they form wide, placid channels across the Deccan Plateau. The largest of these is the Godavari, often called the Dakshin Ganga. Because the entire plateau tilts slightly toward the east, the Godavari follows this gentle gradient straight into the Bay of Bengal. But there is a major topographical anomaly in the peninsula. The Narmada and Tapi rivers flow in the opposite direction, toward the west. The Normata bypasses the eastward tilt of the continent because it sits inside a deep rift valley, a massive fault line created by fracturing Earth. This steep, rocky channel strictly confines the river, preventing it from spreading out to form a delta, and forcing it to dump straight into the sea through estuaries. While the Himalayan rivers use their high energy to actively build new land, the peninsular rivers are locked in place, constrained entirely by the ancient, pre-existing fractures of the Deccan bedrock. When human engineers look at this terrain, they see specific topographical features that can be exploited. Dams are built precisely where the geography provides an advantage. The scale of this intervention is massive. Today, hydroelectric infrastructure laid across these basins generates nearly 46,865 megawatts of power. In the south, engineers utilize the flat, wide peninsular basins to hold immense volumes of water. The Hirakud Dam, for instance, spans an extreme horizontal length to close off the wide Mahanadi Basin. Compare that to the Narmada Rift Valley, where engineers must squeeze tall, concrete gravity structures, like the Sardar Sarovar Dam, directly into the steep confines of the river channel to harness the high-pressure, confined flow. Exploiting the rivers means confronting the materials they carry. A recent study by a United Nations University Institute projects that by 2050, roughly 3,700 Indian dams will lose 26% of their total storage capacity due to severe sediment accumulation. The physics of the rivers are working against the engineering. The exact same natural erosional silt that gives life to the northern deltas is now actively suffocating the country's megadams. Geological constraints dictate the terms of international diplomacy, specifically within the Indus River Basin in the northwest. The 1960 Indus Water Treaty between India and Pakistan is widely cited as a successful diplomatic agreement, but its framework is a direct geopolitical output of topography. This map highlights the three western rivers, the Indus, Jhelum, and Chenab, whose rights were formally allocated to Pakistan. Conversely, the three eastern rivers, the Ravi, Beas, and Setluj, were allocated to India, granting it control. The treaty functions precisely because the landscape allows it to. The physical separation of these distinct tributaries by high-altitude ridges is what made splitting the basin politically and physically enforceable in the first place. Geographic literacy involves identifying the bedrock structures that dictate water flow, draw national borders, and constrain human ambition.